Alright, hi students, welcome to today's lesson which is on the atomic structure. In this chapter itself, it actually builds on a lot on what you learned in the previous topic on the kinetic particle theory. So let's do a quick recap. So in the kinetic particle theory, we state that all metals are made up of tiny particles and these particles are always in constant and random motion. But what exactly are these particles? So these particles could either be atoms, your ions, or molecules. And the focus for this topic is on atoms themselves. Alright, so with that, let's move on to talk about the lesson objectives. So for this part of the lesson, we are going to cover on what are the relative charges and approximate relative masses of the proton, neutron, as well as the electron. Let us take some time to think about what exactly is an atom, and we're going to travel through time and take a look at what exactly happened. In 400 BC, when a famous philosopher, Democritus, first proposed the first ever atomic theory. So he was the one that coined the terms atomos, which means the indivisible piece. How did he come about with this? Basically, according to him, if you were to take an object such as a tree and you were to cut it into half, then cut it into half again, and cut it into half again, and cut it into half again, and then another half. Eventually, you'll reach the smallest possible piece that is no longer divisible, and that itself is atomos, based on what he proposed. So he was the first one to conceive this idea about having a very small particle that makes up all the metals that we see around us. Fast forward to 1803, when you have John Dalton, who is the father of atomic theory. So he proposed that elements in their pure state consist of particles called atoms. And of course today we know that this is not entirely correct because elements can be made up of either atoms or molecules. Then, in 1904, J.J. Thomson proposed the plum pudding model, whereby he suggested that an atom itself actually comprises of a lot of negative charges distributed around this positively charged particle itself. So that was his model during that time. In 1911, Ernest Rutherford, who is the student of J.J. Thomson, through his experiments using the Guilfoyle plum pudding model, he actually discovered that it is not exactly right. In fact, he proposed that the center of an atom is concentrated with positive charge. This is very similar to what we understand today, but according to Ernest, the negative charges are still distributed simply around the positive charge in an evenly distributed manner. In 1913, that's when Niels Bohr came along. He proposed that electrons occupy different levels with different energy. And he's the one that first came up with this model, which you will see very often within your O-level syllabus. So what you see over here is actually a center which has the nucleus, followed by certain circles which represents what we call electron shells. This is the model proposed by Niels Bohr, and it's the one that we will follow throughout this entire lesson. So as you can see, the atomic structure, just something that occupies only one chapter of the textbook, actually took about over 2000 years for it to develop over time. And even till today, the model that we're learning today is still evolving, and in fact, as you go on to higher education, you realize that the Schrödinger electron cloud model is actually the one that best explains what an atom is comprised of. But for this topic itself, we'll just focus on the Bohr's model. So let's come back to the present time. First, let us ask ourselves this question: what exactly are atoms made up of? An atom is the smallest particle of an element that still shares the same chemical properties as the element. It can be made up of three subatomic particles, and they are your proton, neutron, and electron. Over here, you actually see an image of how these particles are arranged. So the proton is the one that is labeled as the positive sign. Neutron is the one that has no charge on it, it's neutral. And your electrons are the green ones that is labeled with a negative sign. Okay, but in reality, we don't usually draw it in this manner, alright? So within this atom itself, you realize there's this center portion that has a cluster of the subatomic particles of the protons and the neutrons. This is what we term as the nucleus, and surrounding it are what we call the electron shells. Like what I said, in reality, we actually draw it in a manner that looks something like this, alright? So instead of having the circular structure, we actually represent them using certain symbols. So in the nucleus, that's where you find your protons and neutrons, and along the electron shells, that's where you have your electrons orbiting around the nucleus itself. So what exactly is the size of an atom? There's this particular video that you can find online which is really very interesting. So basically, if you want to consider the number of atoms that's found inside a grapefruit, or is similar in shape and size to like an orange. So if you were to compare the number of atoms inside this fruit itself, it is actually equivalent to filling up the entire earth with blueberries. So as you can imagine, that's how small exactly is an atom itself. But if an atom is so small, how small are the subatomic particles then? Right, so we'll take a look at a video to show us an analogy about how small the subatomic particles are.
The center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium, with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty! Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit.
So, as you can see from the video, your protons, neutrons, and especially your electrons are actually very, very small subatomic particles that are found within an atom itself. The protons are found in the nucleus. We usually represent it by the symbol P, and it has a relative mass of 1 followed by a relative charge of positive 1. Your neutrons are also found in the nucleus. We represent it by the symbol of N, and it has a relative mass of 1, but however you will notice that the relative charge of a neutron is actually 0. So your neutrons are actually neutral in charge. Then you have your electrons. The electrons are found in electron shells that surround the nucleus, and they're represented by the symbol E with a relative mass of 1/1840, a very, very small number if you key into a calculator, and a relative charge of -1. So that is just a brief introduction to what exactly are protons, neutrons, as well as electrons. So now that you have learned about the 3 types of subatomic particles, let's move on to certain terminologies. So there's these 2 terms that you must know, and they are known as the proton number as well as the nucleon number. In order to understand what these 2 terms means, I need you to take a look at your periodic table, and you'll notice that for each element, there's actually 2 sets of numbers. Am I right? So let's take a look at your periodic table. Alright, so over here on the screen, I actually have a piece of periodic table. It's actually the same as the one that you have at the back of your notes. And if you take a look at this closely, you realize that, let's take a look at, for instance, hydrogen. Okay, you'll notice that there's actually 2 sets of number related to the chemical symbol over there. And you notice that there's this legend over here that shows you there's something that's called the proton number and something that's called the relative atomic mass. Alright, so you have your symbol in the middle followed by the name, and you have 2 numbers at the top and bottom. So let's take a look at lithium. There's a number 3 and there's a number 7. What exactly do this number means? In the periodic table itself, the number at the top represents the proton number, whereas the number at the bottom represents the nucleon number. Alright, so these are 2 sets of numbers that's very, very important and relevant to this part of our lesson. Let's go back and take a look at the notes itself. Alright, so over here, as you look at the notes itself, you realize that it looks somehow different from what you see just now. What do I mean by that? If you take a look at the periodic table, and let's go and take a look at the element of carbon. Okay, so if you take a look at carbon itself, you realize that, hey look, carbon actually is written in this manner, 6C12. Alright, and you notice that the number that I mentioned at the top, this is used to represent the proton number. And the number at the bottom is actually the nucleon number itself. But when you look at the notes that I'm going to show you now, you realize that, hey, how somehow it looks different. Okay, so let's take a look at the notes itself. In the notes, you realize that the numbers are actually being swapped. So the number that you see over here is what we know as the proton number. And the number at the top is what we call the nucleon number. And you have your chemical symbol over here. Alright, so why exactly is there a difference? Now, I need to emphasize to you that this representation is different from the representation that you see in the periodic table. This is what we call an atomic symbol. In an atomic symbol, it still shows the nuclear number as well as the proton number. However, the numbers actually switch as compared to what you see on the periodic table. And that might be very, very confusing. Okay, so the best way for you to remember what exactly do you need to look out for would be to take note that as long as the number is smaller, alright, and that will be the proton number. So do not confuse yourself. Basically, the smaller number will be the number that is the proton number. Alright, with that, let's go back to the lesson itself. So the proton number, as the name suggests, it actually tells you the number of protons that is found inside the atom. Another term that we use to describe it is known as the atomic number. Right. So an atom is always what we term as electrically neutral, because the number of its proton, the proton number, will always be equivalent to the number of its electron. And please take note that this only applies to an atom. It doesn't apply to an ion, for instance. Let's take a look, for example, sodium atom. Okay, can you go to the periodic table and look for the chemical symbol for sodium atom? Right, so if you take a look at sodium, you'll see that there's two sets of numbers. And like what I've mentioned, the smaller number is always the proton number. So let's put a note over here. This is the proton number. And the bigger number will be the nucleon number. And remember, when you were to represent it in the atomic symbol, you have to swap these two numbers. Alright, so you'll look something like this, with 23 at the top and 11 at the bottom, as well as the chemical symbol. Alright, so this is for sodium itself. Let's move on back to the top of the notes. Alright, so this is the representation of your sodium atom's atomic symbol. The number of protons, as you can see from this number at the bottom, is 11. As what I've mentioned just now, the number of protons in an atom is always equivalent to the number of electrons. So for the number of electrons, there's also 11 of them. Now, for sodium itself, it actually has 12 neutrons. We'll talk about how we derive this on the later part. Now, in terms of the total relative charge, for every proton, if you go back to the table that you drew just now, it's actually a relative charge of +1. So if you have 11 of them, that's a charge of +11. Your electrons, -1. So it will be -11. Neutrons is actually 0, is neutral. So even if you have 12 of it, the charge will be 0. Alright. And knowing that you have 11 positive and 11 negative, the overall charge is actually 0. And that's why we say that an atom is always electrically neutral. Alright, in addition to that, every element actually has something that we call a unique proton number. So if you take a look at the periodic table itself, you realize that no two elements will have the same proton number itself. So let's do a quick test. Just take out any rough paper or you can write down on your notes itself. Can you find out what is the proton number for these 4 elements, as well as which element has this number of electrons itself? So you have 1 minute and your time starts now. So, do you manage to derive what are the proton numbers? So you can do a quick check with the answers over here. Right, so over here in this table itself, you realize that there's a lot of practice questions for you to try out. Let me do one as an example itself. For hydrogen, the proton number, notice that this is the atomic symbol, alright? So the proton number is the one that you see at the bottom itself. Okay, so the proton number is 1. Because it's an atom, you have the same number of electrons, and now there's this term known as the nucleon number at the top, and that will give you 1 nucleon. Remember, this is nucleons. Alright, then looking at the next one, nitrogen, you try to look at the periodic table and find out which one exactly is nitrogen. Right, and you have this number itself. Remember, the proton number is a smaller number, so you have 7. Since it's an atom, and the number of nucleons, is represented at the top, and is 14. Alright, so using that, try to fill out the entire table by yourself. For this chlorine itself, you realize that there's a 37 over here. This 37 actually represents the number of nucleons, which is 37. Since it's an atom, if there are 17 electrons and atoms must be electrically neutral, the number of protons must be the same, which is 17. And to represent this chlorine atom, we will use this. Now that we have talked about what is proton number, let's take a look at what exactly are the nucleons number. The nucleon number refers to the total number of protons and the number of neutrons that are inside an atom. So basically, these two are found inside the nucleus. And hence, this term refers to all particles that are found inside the nucleus itself. Another term for the nucleon number is also known as the mass number. And sometimes it's also more informally referenced to as the relative atomic mass. So, like what I've mentioned, the nucleon number refers to the number of protons in addition to the number of neutrons. So with that, if I were to switch around the equation a little bit, the number of neutrons is actually equivalent to the nucleon number subtracting the proton number. Right, because the nucleon number is the number of protons and neutrons add together, the number of neutrons will be equivalent to the nucleon number subtracting the proton number. So let's do a few practice questions and take a look at what exactly does that mean. So over here, I actually have a few unknown elements. Okay, this is not the actual chemical symbol of the elements, it's just a certain algebra. Okay, so W, X, Y, and Z. Right, they are unknown, and you have to identify what is the identity as well as the number of each subatomic particles that are found in it. So let's take a look at how to do this question. Given this atomic symbol, okay, remember that in this entire atomic symbol, the one that is unique to the element itself, remember what is the number? Yes, that's the proton number, and the proton number is always the smaller number. So if you look at this number itself, 26. If you go and take a look at the periodic table itself, and you scan through the entire periodic table for the number of protons that you see over here, 5, 6, 7, 8, 9, and you end up with finding 26, and you realize that it's actually referencing to this element, which is iron, represented by the symbol of Fe. So the unknown that you're seeing here is actually the chemical symbol for iron. So this will be the same thing as writing 56, 26, Fe. Now, in terms of the number of particles, how many protons do you think this particular atom will have? Looking at the proton number, it should have 26. How about the number of electrons? Since atom is electrically neutral, it should also be 26. But now, the number of neutrons. Alright, the number of neutrons, you must be careful, is not 56. 56 is actually the nucleon number. Alright, and this includes both the proton as well as the neutron. So you have to do a subtraction. So the number of neutrons is actually equivalent to 56 minus 26, which is 30. Okay, there are 30 neutrons for this particular element. Now, using the same method, try to answer the remaining questions that you see over here. Okay, you notice certain things that are a little unusual, things that you haven't learned before, and we'll cover some of these in class itself. Now, you might have realized that this particular question that I gave you, 35.517 with a Z, is actually referring to element of chlorine. And you might have derived the number of neutrons as 18.5. This decimal of 0.5, do you think it actually makes sense? Shouldn't the number of subatomic particles be a whole number? How can there be half of a neutron? And actually this comes about because of this concept known as isotopes. So now we are going to explore this concept of isotope by considering a few factors. What exactly is an isotope? Over here I have 3 examples of hydrogen atoms. These are all hydrogen atoms, take note, but if you notice, there are certain differences between them and certain similarities. Can you identify what are they? All of them have the same number of protons, which is 1. They also have the same number of electrons, which is also 1. So what exactly is the difference? The difference is in terms of the number of neutrons. In the first one, there's 0 neutrons. In the second one, there's 1 neutron. There's 2 neutrons. The term that we use to describe such atoms are isotopes. So isotopes are atoms of the same element with the same number of protons and electrons but a different number of neutrons. So everything else is the same except for the number of neutrons. So as a result, the nuclear number will be different from all these atoms. Okay, so you can see over here for hydrogen, the nuclear number that's represented at the top, okay, they are all different because of the difference in number of neutrons. For chlorine, similarly. For elements with isotopes, the mass number that you see is actually calculated based on the relative abundance of each type of atom. What do I mean by that? So because there's 2 types of chlorine atoms, chlorine isotopes, right? In reality, there's 75% of them exist as chlorine-35, which is this one, and the other 25% in the natural world exists as chlorine-37. So how do we calculate what exactly is the mass number? We actually do a simple mathematical calculation based on the relative abundance of each isotope. So the mass number of chlorine will be equivalent to 75% multiplied by 35, which is the mass number of this chlorine-35, followed by 25% multiplied by 37, which is the mass number of chlorine-37, and you end up with the value of 35.5. That's the calculation itself, but how do we explain it if the question were to ask us to do so? Over here, you'll notice that there's a model answer provided for you to take note of. So the mass number of chlorine is 35.5, and you're asked to explain why it's not a whole number. The explanation, there's actually 3 parts to it. First, because chlorine occurs as a mixture of isotopes, and to be more exact, there's 2 possible isotopes. Alright, so this 35.5 that you see is actually a result of an average of the relative abundance of each of the isotopes, and that is how you should structure your explanation in the structured questions. Now, isotopes, besides having similar protons and electrons and different neutrons, you might be wondering, why exactly am I learning about isotopes, right? So isotopes actually have very interesting properties. So they have the same chemical properties, but they have slightly different physical properties. The reason why they have the same chemical properties are due to them having same number of valence electrons. Okay, at this point in time, you wouldn't learn this term yet. So what exactly is valence? Valence just means the outermost electrons. Okay, not to worry, we'll cover this at the later part of this chapter. Alright, however, your isotopes actually have very different physical properties. It's because of the only difference between them, which is the difference in relative atomic mass. This will result in very different physical properties such as densities, melting and boiling points. In terms of melting and boiling point, the heavier the isotopes, the higher the melting point and boiling point itself. Now, isotopes, they actually can emit high energy radiation and are harmful as it can damage living cells and cause cancer. For instance, your barium-137 as well as the iodine-131 are radioisotopes that emit gamma ray. Okay, obviously it's not going to make you become the Hawk, okay, but they are able to release high energy radiation. But if you were to put it into good and safe use, radioisotopes actually have very useful applications. For instance, it can be used to determine the age of fossils, to treat cancer, to be used for nuclear imaging, to be used for nuclear energy. Alright, all these are just a few applications of isotopes if you were to use it correctly.